Himanshu, and in this lecture we will study about the gravitational waves. Now, generally what happens when an electric charge oscillates up and down, it produces electromagnetic radiations. In a similar way, the general theory of relativity predicts that when a massive object, when it oscillates up and down or in any position, it produces a gravitational radiation, or what we call as a gravitational waves. So basically, the gravitational waves are nothing but they are the ripples in the overall geometry of space and time. That's important. Now, some of the cosmic events that produce such ripples are like, star explosion, or maybe their collisions, between the collisions between, the ultra dense neutron stars, or the, the merging of the black holes, or the supernova can be another example. So all these things, they may result in the formation of the ripples in the overall geometry of the space and time. Now, the gravitational radiation is exceedingly difficult to detect because the gravity by nature is much weaker than the electromagnetic radiation, and that is why it is always difficult to detect these things. So the question lies that, how are they produced? Actually, so in 2016, we have, the first gravitational waves were discovered, and in 2016 they were actually observed from the merger of the two neutron stars. So merger of two neutron stars. So the two neutron stars rotate around each other. Closer they get, the faster they spin, and eventually they collide. The energy from their spiraling and the merging releases energy in the form of the gravitational waves, or the ripple in the space and time. Now, the only thing is that, so what is the significance of the discovery? That is the major question. Now, the discovery of the gravitational wave is the beginning for the new era in astronomy, because this, so far all the observations of the universe are made through the electromagnetic radiations emitting from the object, from the visible light to the gamma rays. The gravitational waves are actually the new one. By seeing what happens in space, we can now detect events that, that would otherwise leave a little to the no observable light, like black hole collisions. So it will also help us to untangle the mysteries about the dense, dead objects, which are called the neutron stars, that we have discussed before. So that is mainly about the gravitational waves. The next thing that we're going to discuss about is the LIGO. As we know, the LIGO, that the Gravitational Wave Observatory. So this is what it basically does. It does the same thing. It measures, it keeps a track then when the next gravitational wave will come. So this is what it does. So it has been designed directly to detect the gravitational waves. So in 2017, for the first time, the scientists directly detected the gravitational waves from the collision of the two neutron stars using the US-based, the LIGO. The LIGO is basically full form is the Laser Interferometer. Let me write it here. Laser Interferometer Gravitational Wave Observatory. That is basically the Europe-based Virgo detector and some 70 ground and space-based observatories. So the LIGO detectors use the laser interferometry to measure the even the minute ripples in the space and times from the merger of the pair of neutron stars or the black hole or the supernova. So till now, I think the LIGO has detected the gravitational waves twice now, and the second time they're witnessing the merger of the second black hole pair. The signal from the merger was weaker actually than the first one, but it was still good. So hence that spiral technique is what we call as a matched filtering was adapted for the gravitational wave data analysis, which was developed by the IUCCA Pune. The same concept the Pune has also made, and recently we also have a LIGO-India. We also call it as sometimes as the IndIGO. IndIGO, that is basically the Indian initiative with the gravitational wave observation. It is a consortium of the Indian gravitational wave physicists to set up the advanced experimental gravitational wave observatory in India. So actually the LIGO-India is planned advanced gravitational wave observatory, and it is currently located in the Aundh. The region is important. So it is in the Aundh region, AUNDHA. The full name was Ong Nath Nath, I think. Ong Nath Nath in the Hingoli district in Maharashtra, I think. Yeah. So Maharashtra. Now this is important because it was in the news. Now the next thing that we're gonna read about is the LISA Pathfinder. Now it is basically the short for the laser interferometer space antenna. Laser interferometer space antenna, and the mission was actually led by the ESA, that is basically the European Space Agency, to build the space-based observatory for detecting the gravitational waves. So like the LIGO was actually of the ground level, but the LISA Pathfinder will be in the space itself. So this is the only difference. The LISA Pathfinder will be in the space and the LIGO will be on the surface. So it will do the same work as it was doing. So that's basically about the LISA Pathfinder. The next one that we're going to talk about is basically the CERN. You must have read about a lot regarding in the newspaper, because the Hindu generally publish one or more article in every fortnight regarding the CERN. Now the CERN is basically stands for the European Council for Nuclear Research. European Council for Nuclear Research. It is basically the world's largest nuclear and the particle physics laboratory. So just mention it somewhere that it is the the largest in the world nuclear and particle physics laboratory, with the mandate of establishing a world-class fundamental physics research organization along the around the France-Switzerland border. So it's near Geneva. We can't trust UPSC these days. There's some, so yes, it's in Geneva. No matter, they can ask anything. So at CERN, the fundamental particles of the matters are made to collide together at a speed of light, giving the physicist the clue about how the particle interact at such a high speed, and provides an insight into the moment of creation of a universe through the recreating a Big Bang. So in short, they create a Big Bang in their laboratories, like how everything happened by colliding the particles together with the speed of light. So at present, the CERN has 22 members, and CERN usually have members dividing as there are observers, there are associate members, and there are, I think, observer states, and there are also observer international, and these are the observer states. Now India earlier was an observer state, but now the India has given a status for the associate member in 2016. So this is pretty much important. Now India is an associate member. Now we can also contribute to their research, and we can also benefit from their research. Apart from that, the next one we're going to read about is that a KUIPER Belt would be a good one. Now the KUIPER Belt actually extend from the 30 to 50 astronomical units, 30 to 50 AU, you know, the astronomical unit is basically that's important. Yeah, AU. So 1 AU is actually equal to the distance between Sun and Earth. That's important, you know. So 1 AU is actually the distance between the Sun and Earth, and the Kuiper Belt is extends from 30 to 50 AU. So when the solar system was young, you know, a large number of icy, you know, the planetesimal was formed in the region beyond Jupiter, right? So the gravitational force of the massive Jovian planets, Jovian means the gaseous planet, right? So the gravitational force of these Jovian planets pushed most of these planetesimal beyond Neptune's orbit, concentrating them into the belt centered on the plane of the ecliptic called Kuiper Belt. So if I say that, you know, we have like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So, you know, after this thing, so here there will be a one belt. That one belt is basically consists of the huge number of asteroids here, and this basically what we call as a Kuiper Belt. Now the objects in the Kuiper Belt are also called the trans-Neptune objects of the Kuiper Belt objects. Trans-Neptune objects, you know, pretty much same. So the object within the Kuiper Belt form the most primitive object from the beginning of the formation of a solar system, and most of the comets also have their origin in this Kuiper Belt. So thus the Kuiper Belt is a laboratory for studying the well-preserved, you know, the primitive material from the planet, which are actually the 4.5 billion years old. So it's a huge, you know, we can, if we study them, then there's a huge knowledge that we can gain regarding our solar system. And there are a few words like, you know, the exoplanets, and you should know the exoplanets are all the planets which are outside our solar system. So this is what we call the exoplanet, and we have already discussed of the Goldilocks zone. There is also in the news recently that's called the Plunet. Sorry.